Good morning, everybody. Welcome to the latest edition of the Pangolin Seminar. Today, Matilde Martínez García from the Universidad de República in Uruguay is going to speak to us about tilings, amenable equivalence relations, and foliated spaces. So, over to you, Matilde.
Thank you very much. I want to thank the organizers for the invitation. This is a wonderful seminar and it's wonderful to be speaking here. I don't know if you can see the presentation.
Yes, we can. Okay. Yes, we can.
Okay, so I'll try to keep it informal, so please feel free to ask questions, to interrupt. I'm not the kind of speaker who is very serious about saying absolutely she has prepared everything she has prepared. So I'm going to modify the talk according to everyone's interests. Okay. So this is joint work with Fernando Alcalde and Álvaro Lozano, both from Spain, from Santiago de Compostela and Zaragoza. And the plan for my talk is the following. I'll start with two motivating questions. Then I'll speak about the space of tilings. I'll describe a particular tiling or a particular family of tilings on a Lie group called SOL-AB, which of course I'll present. I'll speak about the continuous hull of this tiling and I'll describe its foliated structure. And then I'll speak about something which will be clear at the end, I hope, which is about an amenable equivalence relation, which is not affable. So all these words will be introduced more or less. So the two motivating questions for this work are the following. The first question is a question by Gilbert Hector, who posed the following problem. You have a compact metrizable space with a foliated structure. There's what we usually call lamination. A lamination on a compact space, so leaves are not necessarily compact. And the question is, are the leaves of F quasi-isometric to Cayley graphs? So what Hector was asking is if this was always the case. So if foliated spaces, compact foliated spaces have always this property that their leaves are quasi-isometric to Cayley graphs, that is to finitely generated groups. And this is known to be true when the generic leaf has two ends through a combination of results involving...
So Thierry appears to have a question.
Okay.
Thierry?
Yes, I just wonder, in the question of Hector, it just means all the leaves are quasi-symmetric to the graph of some group.
Yes.
But does it claim that it is all the groups are quotients of a common universal group?
No, like I understand that what he asked. I'm not very familiar with the context in which this question arose. So, but I understand that what he's asking is, he's stating that probably leaves cannot just have any type of growth. So the type of growth is that of a Cayley graph of some group. That's what I understand the question to be. But again, I don't know the exact context in which this question arose. I do know that he was interested in a particular case where all the leaves had a Cantor set of ends. So the answer to this question is known to be true where the generic leaves have two ends. And as you'll see today, I'll be presenting an example of a foliated space where all leaves have one end and they are not quasi-isometric to a group, to a finitely generated group. So the answer of the question would be no in any variant of the question for leaves with one end. And the problem is still open for a counter set of ends, which I understand there's a problem Hector was really interested in. I don't know if I've answered. No, I haven't, but I mean. Well.
Okay.
Sorry?
Okay, thanks. No, I was just thanking
okay.
because I think we all.
So the second motivating question is a very, it's a deep conjecture by Giordano, Putnam, and Scow, which I'll call GPS, which is the following. If you have a countable amenable group acting continuously with a free and minimal action, which means that there are no stabilizers, that is free, and minimal means all orbits are dense on the counter set. Is that always orbit equivalent to a minimal action of the integers on the counter set? So this question is part of a much broader problem, which is the following. So if you have a group acting on a set, of course, this defines a partition on the set, or which is same, an equivalence relation on the set. And the broad question is, what properties of the group can you read in this equivalence relations? So you see the group acting in different spaces, and thus the structure of the equivalence relations it generates capture some of the group properties, algebraic or geometric properties. So this is a topic that has been widely explored, and there's a very well-known theorem by Kohn, Spellman, and Weiss that says the following. It's in the measurable category. So you start with a standard Borel space, say, for instance, the interval with the Borel sigma algebra, and a Borel probability measure on this space, and you have some equivalence relation on this space, measurable Borel equivalence relation, which is countable, and that means that it has the equivalence clauses are countable. So the following conditions are equivalent. So this equivalent relations arises from an action of the integers, a mu measurable action of the integers. And for any amenable countable group G, there is a measurable action that induces the relationship. So the equivalence relation thus captures the fact that the group is amenable, but does not distinguish among different amenable groups. So in this setting, for the equivalence relation is the same for whether the group is C or is not C. So you cannot read in the relationship whether you have a C action or you have an action of another countable amenable group. And in fact, the theorem says more. So the equivalence relationships that have this property have a very simple characterization. It's what it's called hyperfinite equivalence relationships. So this is just they're generated by finite partitions. So they have a simple characterization, and every time you have a hyperfinite equivalence relations, you can say that not by a finite partition, by finite equivalence relations. So every time you have an equivalence relation of this type, you know that for any countable minimal group, there's a measurable action inducing this particular relationship. So Giordano, Putnam, and Scow tried to do something similar in the continuous category. So they looked at topological spaces and continuous maps. And of course, you have nothing which is something so general as a standard Borel space. So one example of something that yields a Borel space is Cantor sets. And this is a particularly rich example because it has a kind of universal property in the sense that any dynamical system, so any Z action on a compact metric space is a quotient or factor of the any minimal C action on a compact metric space is a factor of a minimal dynamics in the Cantor set. So this is a very, very rich family of dynamics, the minimal actions on the Cantor sets. And they asked themselves whether the equivalence relation induced by any a minimal group, countable minimal group, when you have a free continuous action, is the same as is also induced by an action of a group C. And this question is open, but they were able to characterize minimal C actions in a way which is similar to the Kohn-Feldman-Weiss characterization of amenable actions as inducing hyperfinite equivalence relationships. And they proved that minimal C actions yield what they call affable equivalence relationships, which I'm not defining right now. We'll go to the end of the talk, but it's a condition in the topological setting, which is similar to being hyperfinite. So this is a second motivating question, which is very deep. Giordano, Putnam, and Scow have solved it for many groups, for free abelian groups of finite rank, for instance, and the answer so far has been positive. So what I will do in this talk is I'll be constructing an example of some foliated space coming from somewhere. And I'll be starting with a tiling. So I'll be speaking about the space of tilings. So probably you already know what a tiling is. Here we see pictures of two tilings of floors. One is a tiling by two different squares, and another one is a tiling with different kind of tiles. I think that it has two tiles, which are quadrilaterals. And many of you will have recognized Sir Roger Penrose on the second picture. We'll be speaking about him shortly. So how do we define informally?
Will you be speaking about Penrose tilings then?
I'll be speaking about one particular tiling, which is an example constructed by Penrose, but not about Penrose tilings in general.
Okay.
Mm-hmm. So, but yeah, Penrose and tilings are two words that often go together, yes. So, I'll define informally what a tiling is, okay? So, what property does it have? First of all, it has a finite number of tiles. It covers a space with no overlaps or gaps. And it can have many different properties. For instance, we speak about periodic tiling when it has a repeating pattern. This means that there's a compact set where you have finitely many tiles, obviously, in a certain pattern, and then this pattern just repeats itself. So, for instance, this tiling on the left is a repetitive tiling. The one on the right is not. Periodic tiling. And aperiodic tiling is not the same as a tiling which is non-periodic. And aperiodic tiling is one that does not have any translation, which leaves it invariant. So it has no symmetry at all when you apply translations. So it's not the exact opposite of being periodic. A repetitive tiling is a tiling that looks very much like itself in many places. So the exact way of saying this is for any radius r, there is a bigger radius r prime, such that any ball of radius r has an exact copy in any ball of radius r prime. So this is, you have many places that look like each other, and uniformly, you have them uniformly distributed. And then you can ask on some condition on how the tiles intersect. So they cannot overlap, so two tiles are either disjoint or they touch in their boundaries. And you usually ask for the gluing to be face-to-face. So the intersection of two tiles which are not disjoint is the one of the faces of each of them. So for instance, this tiling on the left is not face-to-face. And the tiling on the right is face-to-face. But the important property is really not that it is face-to-face, but you do impose some condition on how the tilings, the tiles are put together, because this will impact the topology of your space of tilings, okay? So you usually have some condition that involves some local finiteness of the combinatorics. So, and I am speaking about tilings on Lie groups. So everything I said, you can do on a Lie group. So finite number of tiles, no overlaps or gaps, and some condition on how faces touch. So what is the space of tilings? You fix your finite set of tiles, and the elements of this space are the tilings with a marked point. So that there's a position which I'll be calling O. And you say that two tilings are close if big balls centered at O are close in the sense that they differ by an isometry which is close to the identity. And this is a topological space, and the Lie group G acts on this space by translation. So by just moving the origin around by translations. And we say that the continuous hull of a tiling, it's the closure of its G orbit. So these closures can have many things. For instance, if we tell the floor, the plane R2 with squares in the most usual way, that's periodic tiling. But for instance, if we break one of the tiles, cutting it in half, that will give a tiling with two different tiles, say a square and two small rectangles or triangles according to how we've broken this down. And this is no longer periodic. In fact, it's no translation other than the identity leaves it the same. But when you act back by translation in its closure, you have the periodic tiling again. So you move the tile which is different to infinity, and you get the periodic tiling in the closure. So many things can be in the continuous hull of a tile, but of a tiling. But when the tiling is repetitive and aperiodic, every other tiling in its continuous hull is also repetitive and aperiodic. And the continuous hull has a foliated structure. So the Lie group G acts there. It's a saturated set by the action. It has a structure of a foliated space or lamination, which is transversely canter. So the leaves are the G orbits, and it's transversely canter, and all leaves are dense because all points are repetitive tilings, and all leaves are equal to G, let's say, because all tilings in this continuous hull are aperiodic. So this is the kind of object we'll be constructing. So the group I'll be speaking about is this solvable Lie group called Sol AB. We start with two real numbers, positive real numbers A and B. And so Sol AB is a three-dimensional Lie group obtained as a semi-direct product of R2 and R, defined by the following action of R on R2. C, a point in R, acts as this matrix acting linearly on R2. And that is the same. Maybe I've forgotten something. No, it's the same as this. So this is this group of matrices, okay? This is how you can see it as a subgroup of GL3R. So when A is equal to B, you get essentially, well, first of all, this is a two-parameter family of groups, but they are not all different. So, but they are different, which is not obvious, maybe. But what is crucial is the ratio B over A. Okay? So it's really a one-parameter family of groups. And where A is equal to B, you get the Goodenold Sol, which is this. So what does Sol look like? This is Sol. It has two transverse families of hyperbolic planes. So I marked in yellow one family of hyperbolic planes. I'm looking at Sol as a Riemannian manifold with a left invariant metric. So I've written there a metric which is left invariant. And in yellow, I've marked one family of hyperbolic plane, and in blue, I've marked another transverse family of hyperbolic plane. So I tried to draw a picture. So here, the white line is the C direction, and you have to think of the blue planes as being hyperbolic plane in the log model, where infinity is upwards, and the yellow hyperbolic planes are also hyperbolic planes, say in the log model, but upside down, so the infinity is downwards, okay? So that means that when you go up the white axis, you have one direction, which is contracted, which is the blue one, exponentially contracted, and the yellow direction, which is exponentially expanded. Okay. And what is Sol AB? Well, it's the same, except that you tweak the rates of expansion and contraction of the yellow and the blue planes. Okay. And this gives a group which is still a solvable group. It still has these two transverse families of hyperbolic planes, or of planes of a negative curvature. But it's, for instance, no longer a unimodular. So it does have different properties. For instance, Sol has many lattices. And so AB, being non-unimodular, cannot have a lattice. Okay. So, and when B over A is different from B prime over A, these are really different groups. So in our construction, we'll be following Samuel Petit's work. He has a very nice paper in ergodic theory, which is his thesis, called On Invariant Measures of Finite Affine Type Tilings. This is a paper I've always liked a lot. I got to know this work when I met Samuel, when we were both PhD students. I met him in Dijon, and he was speaking about these things, which I found fascinating, but I then devoted myself to doing other things completely. So it's very nice to finally come back to his ideas and follow through on some of them. And what Samuel does, so anyone who knows Samuel's work will see that this is very similar, okay? And what he does is he works with tilings on the affine group of the affine transformations of the line, which is the simply connected two-dimensional Lie group, which is non-abelian. And what we do different is, the reason why we work with Sol AB is the following result by Eskin, Fisher, and White. If A is not equal to B, that is, if this group is not Sol, Sol AB is not quasi-isometric to a Cayley graph. So, of course, if a Lie group has a compact lattice, it's quasi-isometric to a Cayley graph of this lattice. But the affine group, the group with which Samuel worked, does not have any lattice, but it's with the left invariant metric, it is isometric to the hyperbolic plane and is therefore quasi-isometric to any co-compact Fuchsian group. So it does not have this particular property we're interested in. So the reason why we chose this group Sol AB is that they have this very fine property of not being quasi-isometric to Cayley graphs. One minor comment is that if we chose A and B as being of opposite signs, we would get a group from another family, which is called the Heinze group. And these groups have negative curvature. They also are non-isometric to Cayley graphs, and we would be able to do the same construction. Not to get the same punchline at the end related to the GPS conjecture, okay? So we chose these particular groups because they have two nice properties, which is that they're solvable and therefore amenable. That's the one thing we're interested in. And the other one is that they're not quasi-isometric to Kitty graphs. So we'll construct a tiling on this group. We start by the tiling of the hyperbolic plane, which is due to Penrose. And this is where Penrose come in. It's the following thing. It's drawn here. So it has only one tile P, which is drawn there. And then we push this tile with two transformations. First, we translate it horizontal with this thing, which is called S. That is simply a horizontal translation by 1. And once we've obtained a horizontal line of tiles, we push it upwards and downwards with R and R minus 1. So R is this thing which sends C to 2C, okay? It's both are, of course, isometries of the hyperbolic plane. And this gives a tiling of the hyperbolic plane. There's nothing magical about the shape of this tile, so Penrose could have done the same with a square. The reason why it's not a square is that if it were a square, it wouldn't be face to face. So this funny shape just means that Penrose has kind of artificially introduced a vertex in the lower face of the tile to make the tiling face to face. Okay. So this tiling is not periodic and it's not aperiodic. And it clearly has a symmetry. R is a symmetry. So I don't know if yes, here I've written what the tiling is. So the tiling is the initial tile P, then you push it by some iterate of S, and then you push it by some iterate of R in that order, okay? And this tiling is clearly not periodic because it has a symmetry R. And I was speaking about tilings and Lie groups. And the thing is, the hyperbolic plane is isometric to the affine group with a left invariant metric. And you can realize all this with in the affine group with translations and so on. So you can really see these things, put these things in the Lie group framework I presented before. So we break this R symmetry. We color the tiling to break the symmetry. Coloring or decorating, we generate two different tiles or any finite number of tiles. And we can do this in a way which makes the tiling aperiodic and also recurrent. So there are many ways to do this, and Samuel explains that very well. So now we have a repetitive and aperiodic tiling of the hyperbolic plane, or equivalently the affine group. So we want to use this to build a tiling on Sol AB. So Sol AB can be seen as the R3 space with a metric, which is this metric. It's the left invariant if you write everything in the appropriate coordinates, which I have probably not done correctly because, well, you know. So two transverse family of hyperbolic planes, the one which were yellow and blue, and I've tried to show this with the underlining, so the different coordinates that can get contracted and expanded exponentially when z goes up and down. So let me choose one of the yellow hyperbolic planes, say the yellow hyperbolic plane that passes through the origin in R3. And I will draw Penrose's initial tile P in this plane. So I'll draw it in yellow, it's right there. And now we want to fatten P along the direction, the blue direction, which is Y direction, okay? So we do this in the following way. We have this flow that flows in the blue direction, which is simply left translation in this group by the element 0s0. And it gives this, okay? And this, when we flow time 1, we have succeeded in fattening the tile P to get P hat. So that's what I've written here. Are there any questions?
So far, no. But so these tiles, they also join up in Sol without any problems.
Yes, yes. You can do this in Sol without any problem. Yeah.
Because am I understanding correctly that the amount by which you fatten the top will be less than the amount by which you're fattening the bottom, heuristically speaking? Is that right?
I'll have a picture later on how they fit in.
Okay.
So this is one tile I'm fattening. Okay. And the problem is when they start to move up and down, this thing which you're saying will happen, yes.
Okay, okay.
I'll show a picture.
Great.
So they'll be fitting like Lego bricks.
Okay.
You know, sometimes you put 2 or more and so on.
Excellent.
And that's when the condition on how faces should touch. When you want to impose it, not any group will do, okay? Okay. I'll get there. So we have this fat tile, and then this is the initial tile for a tiling in Sol B. So to get to tiling, we're going to translate this P hat tile just as Penrose did, but we have to translate it along 3 directions. So one direction is this blue direction along this flow, the time 1 of this flow TS, which I've previously called the horocycle flow on the blue plane, because it's if you think of in the blue planes of C as being the geodesics, this is the direction which get expanded and expanded and contracted. Okay. So one is this transverse blue direction along this, say, horocycle flow. And then we have S and R, the S and R in the Penrose tiling, we can extend them to push things upwards and downwards and to the side in the yellow direction. And they get, you can extend them to this, for instance, R hat, which is the left action by this element, 0, 0, log 2 over A. And this gives you this. And this moves also, as you said, the Y coordinate in this way. Okay, and S hat is similar. So you really do a lot of translating in the group. So these are left translations in the group. And you get this tiling, which is first you translate by T, then by S, then by R, some iterates of this in this order. And what we prove is that doing this, you get a tiling of Sol AB. And here I'll be addressing your question. So when you apply this S and R thing, so here is R, for instance, the original tile P hat, when you push it upwards, gets thinner. And when you push it downwards, it gets fatter. So if you want a tiling which is face-to-face, you have to have some condition on A and B in order to be able to build this from, say, finitely many Lego bricks in each place. So the vertices cannot just be anywhere. And of course, when you have this, you can, if you want it face to face, you can do just as Penrose did. You just put some vertices in the appropriate places by hand. So the theorem says the following: if B over A is log n over log 2 for some integer n, then this tiling T hat is face to face and repetitive. And it's not aperiodic because Penrose's tiling was not, but you can color it. You can color it in order to make it aperiodic. So in the same way you can build a tiling in the affine group following Samuel Petit, we build an aperiodic repetitive tiling on this group SOL AB. So I have, how long is this?
You still have 20 minutes.
Ah, okay, great. And this is how this tiling looks like. So now we go to the space of tilings. We fixed the tiles, which now we probably have 2 tiles because we've introduced a coloring. And in the space of tilings of the group SOL AB by these tiles, which is of course non-empty because we have constructed an example, we have a SOL AB action by translations, and the orbit closure of this particular tiling we have constructed is what we call its continuous hull. So now we'll be sticking with this restriction that B over A is of the form log n over log 2. And we'll call MAB the continuous hull of this tiling we've constructed. And it's a compact matricial space, which is saturated by the SOL AB action. So it's a compact matricial space, compact metric space, in fact, endowed with a continuous action of the Lie group SOL AB. And it turns out that with the foliation given by the orbits, it's a lamination which is transversely cancer. And since we started with a tiling which was aperiodic and repetitive, everyone in its orbit closure turns out to have the same property, and the action of SOL AB in this space, MAB, is free. So the leaves of MAB are essentially copies, metric copies of SOL AB. So they are not quasi-isometric to Cayley graphs due to the results by Esking, Fisher, and White, which stated that SOL AB was not itself quasi-isometric to a Cayley graph.
So just a second. So you're saying that the leaves of this lamination, all the leaves of this lamination have uniformly negative curvature, negative sectional curvature?
No, they don't have a uniformly negative curvature.
Oh, okay.
Because
doesn't SOL AB have uniformly negative curvature?
No, it doesn't.
Oh, okay. Sorry.
SOL doesn't have uniformly negative curvature.
Okay, I misunderstood. That's okay.
So no, I'll go back to SOL. The thing is, let me see here. So if you erase this minus sign down here.
Which one?
The E to the minus B whatever.
Okay.
So what you have is that as C grows, you have two directions which are expanded, and both the blue and the yellow directions are exponentially expanded.
Okay.
And that's very similar to a hyperbolic 3 space. So this does have negative curvature, and this gives other groups, which are called the Heinze groups, which are negatively curved.
Right.
So I like them because I like negative curvature. I'm very much a negative person.
Right.
So in fact, this is my first close acquaintance with a group which doesn't have negative curvature.
Right.
But actually Sol has some positive sectional curvatures.
Oh, right, I see.
So, and Sol AB as well. So yes, these are not negatively curved.
Okay. Okay.
So also the Heinze groups, which would be the ones with negative curvature, which you get when you choose the signs in a different way, those are also not quasi-isometric to kilograms.
Mm-hmm. So,
and we could do the same construction there.
So you can construct these tilings for Heinze groups as well, and that would give you laminations with negatively curved leaves.
Yes. Yes.
Oh, okay, that's
exactly.
interesting. That's interesting.
Yes.
Sebastian knows why I'm interested in that. Thank you.
Yes, you can do the same thing. Yes. If you like negative curvature, you just change the sign. But we like amenability. So okay. So this gives a negative answer to Hector's question. So you do have compact foliated spaces which have leaves which are not quasi-isometric to kilograms. And now I'll go to very, very briefly, because my time is almost over.
You have 15 minutes.
15? Ah, okay. Yeah. I thought I had until, okay. Okay. So to the, what I call the GPS conjecture, the conjecture by Giordano Namaskau. So I'll recall what this conjecture was. So if you have a countable and amenable group acting freely and minimally on the counter sets, the question is whether this action is always topologically orbit equivalent to a Z action. So being topologically orbit equivalent means that you have a homeomorphism from X to itself that sends G orbits into Z orbits in any way. And this is the question, it's wide open, and it has a positive answer for finite rank pre-abelian groups, so C to the M. So this is a question inspired by the Kohn-Feldman-Weiss result in the measurable category. So here I'll lie to you a little bit. I'm saying some zero measure lies, okay? Because you see that I have the standard Borel space XB and the Borel measure mu, and the measure is important, but I'm not saying how the measure, I'm not speaking of the measure, so there's a zero measure lie here, so don't use me as a reference on this topic, that's what I mean. So the equivalence relation, the Kohn-Feldman-Weiss results says that for the equivalence relation, it's the same to be what is called an amenable equivalence, which has a definition. That's the same as being hyperfinite, which is something that also has a definition, which is very simple definition. And this is the same as being the relationship induced by the action of some amenable group G. And you can choose any group. So for any countable amenable group G, there's an action that will give you this relationship. And this is the same as being induced by some C action, so by some dynamical system, okay? All these things are the same. So in the measurable category, there's very little you can say by looking at the relationship itself, but the relationship does tell you if it comes from actions of amenable groups. So amenability is something which can be read in the relationship, but different amenable groups cannot be distinguished from the partition given by the orbits. So, so Giordano, Putnam, and Scow in this continuous setting in the counter set proved that if you have a minimal equivalence relation, that means that all equivalence classes are dense in the counter set. It's the same to say that it's induced by a dynamical system, so by a continuous action of the integers. They've characterized this as the relationship being affable, which is a condition that we can see as a kind of equivalence or analog, not equivalence, analog of hyperfiniteness in the topological setting, but it's not so easy to define, okay? It's being a limit of Klopen equivalence relationships and so on. So I don't want to get in there, but there is a condition which can be stated not in terms of actions, but of partitions, let's say, which is equivalent to coming from an action of the integers. So affable means AF, able, and AF means approximately finite dimensional. So the questions which are open are, is this equivalent to the relation being amenable? And does this mean that the relationship comes from a continuous action of an amenable group? So this is what is open and very hard indeed. So wait a minute, what? Okay. No, so this is what I want to say. So if you start from an amenable group acting on X, sorry, no, okay. So if you start from an amenable group acting on X, that does imply, and this is the arrow to the right, that the relationship you get, the equivalence relationship given by the orbits, is an amenable equivalence relationship, which is something I have not defined, but it's. So, and the Giordano-Putnam-Scow question or conjecture is the following, is the green arrow is if having an amenable group acting on X is something which is orbit equivalent to having, topologically orbit equivalent to having C acting on X, X being the counter sets and the action being minimum. Sorry, I forgot to write that, okay? And what we do with our example of the tiling, and I'll say what the relationship is exactly in a minute, is showing that the green arrow, let's say, cannot be factorized through the white arrow. So what we do is we construct an amenable equivalence relationship which does not come from an action of the integers. And which is this equivalence relationship? It's the following. So the Cantor set we're working with is a transversal of our foliated space MAB, which is a continuous hull of the tiling. So the relation is simply belonging to the same leaf. So when 2 points in the transversal belong to the same leaf, we say that it is that they're equivalent. And this relationship is amenable, and I won't explain how you prove this because I haven't defined an amenable relationship in the first place. But this is something which comes from the fact that we've somehow constructed this from the action of an amenable Lie group. So this equivalence relationship in the Cantor set mirrors many properties of the foliated space MAB that comes from a Lie group action and an action from a Lie group which is an amenable Lie group, okay? And the reason this relationship is not induced by a C action is because MAB does not admit a transverse invariant measure when A is different from B. So actually explaining this, so the first thing which is clear is this is very far from giving a negative answer to the GPS conjecture, but I hope it somehow shows that the GPS conjecture is very subtle and that it's really a conjecture about how groups act and it can't be easily reduced to a statement about equivalence relationships. And there are some measures zero lies in everything I've said because there are measures. But if I wanted to explain all this, I'll have to speak about some other aspect of the word, which is the ergodic properties of these foliations we have constructed, which we called MAB. So basically, this is the last slide. The important ergodic properties we proved are the following. So if you're familiar with Samuel's work, this won't be surprising. A measure on the space MAB is harmonic with respect to foliation if and only if it's invariant by the action of the Lie group Sol AB. And the measure is totally invariant, that is, it comes from a transverse invariant measure if and only if A is equal to B. So that means that the group you're acting with is actually good old Sol. And in no other case are there holonomy invariant measures or totally invariant measures. And this has to do with the fact that when A is different from B, the Lie group Sol AB is not unimodular. So any space where you have such an action will be a foliated space that does not admit holonomy invariant measures. So this would be another talk. But these properties of the equivalence relation given by the belonging to the same leaf and the transversal, these properties come from an analysis of the harmonic and invariant measure on the foliated space MAB. And one final remark for those interested in harmonic measures and so on, is that this space MAB can be, for instance, uniquely ergodic in the sense that it has one harmonic measure, or it can have many harmonic measures depending on how exactly you color the tiling. So there are many choices we've made here, and you can trick the tiling to to get a uniquely ergodic foliation or a foliation that has many harmonic measures. So thank you for listening.
So thank you very much. Please unmute your speakers, everyone, so that we can thank the speaker. Excellent. Thank you very much, Matilde. So does anybody have any questions?
Maybe I have a question.
Please,
yes.
Please, Sebastian.
So very nice talk. I enjoy very much the result. Does your group sol AB it is not unimodular, but does it have some quotients with infinitely many ends or something like this? We were trying to talk with I don't know, when Fernando sent me your paper. I tried to try to talk a little bit about what could you have such an example with the leaves with infinitely many ends?
Yeah.
Yes. So I was thinking like maybe you can try to play ping pong inside sol of AB. Maybe try to find isometry that can try to play ping pong and try to play the same game as you played. But this I never looked inside the isometry group of sol of AB. I don't know how it is.
No, I had never thought about that. No, I think it's a very interesting question, but
because it could be like
I had never thought about it. But maybe yeah.
You try like starting from a Schottky of the hyperbolic group, some tiling invariant by the Schottky, try to push it as you push the tile, and then try to see if you can obtain some leaf with infinitely many ends, which is not a tree, it's not a Cantor set. And so this was maybe an idea, but I didn't
so maybe
think...
the baby case would be try to tweak Samuel's example to do this.
Yes, maybe. Maybe it could be
to get something in the affine group, which
you're right. How do you? Well, so I don't know. So this is
yes, we should definitely.
And I don't know if in the Einstein group either if you have how are the quotients of this kind of three-dimensional Lie groups? I don't know. You don't have compact quotient, but maybe you have more interesting quotients some way. So this was a question. I don't know.
Yes, it's a great question. I've never thought about it.
So, if I may ask, so I'll start with perhaps a silly question. If I understand correctly, then the space of tilings for any given set of tiles, just viewed as a topological space, ignoring for the moment the orbit, it's not a very nice topological space, is it? You can't make it look like a Teichmuller space. It doesn't have a local Euclidean structure.
No, in fact, it's a very classical example of a non-commutative space. If you read the Kohm's book on non-commutative geometry,
I was going to ask.
One example in chapter 1
right.
is that.
I was going to ask about that.
So it's very horrible.
Right.
Horrible, and also the Gromov-Hausdorff metric, which I described, is not a distance. So, for instance, for a periodic tiling, you have things at distance 0 if you define it exactly as I did. So you do have to get some quotients. And yes, and it does get nasty. Yes.
Right. So, I mean, given that you mentioned Kohn, this is stuff. It's a stuff related to the study of von Neumann algebras. Then.
Yes. Yes. That's the part which I find very hard.
Me too. Me too. I'm just reading
yes,
about them at the moment. It's fascinating. But
yes,
very, very difficult.
And when you try to understand these things of amenable equivalence relationships and so on, and get into the Kohn-Spellman-Weiss theory, you very quickly get into the language of von Neumann algebras.
Right.
And that's so many of the relevant references have this very well, this language which
Very esoteric.
I'm starting in this topic, so
Right.
this is my first tiling ever, and this relationship to non-commutative geometry is one of the reasons why I find the subject very challenging.
Okay.
It's really interesting.
I have a more down-to-earth question. Is the harmonic measure related or relatable to random walks along the edges of these graphs that you construct?
That's a very good question.
You could try to discretize the harmonic measure and try to find some kind of discrete process on the contour set.
Yes.
And this you could try to see, maybe this is a good question, I think. I don't know, Matilde, sorry.
Yes, I was thinking that if any old way of discretizing the Brownian motion will give you essentially the same thing, so, or if the lengths of the edges somehow matter.
But you can make these tiles arbitrarily small, can't you? Actually, that's kind of meaningless.
Yes.
So you can approximate the Brownian motion with
the Brownian motion. Yes.
Oh. Might be interesting to see if the random walk converges to the. It shouldn't it? I'm no expert in this field.
It's very, very interesting.
Right. Well,
kind of tilings here.
Are there any other questions? Does anybody have any other questions? I should add, it was a lovely talk, Matilde. It was very clear, which makes it hard to ask hard questions because you explained everything during the talk. But are there any other questions, anybody? So I don't think there are any other questions. So everybody, please unmute your speakers and let's thank Matilde once again for what was a lovely, very interesting.
I find it very hard to give talks where you don't see the faces of the.
I know. It's very disconcerting. Now, just give me a minute, everybody, so that I can advertise the next edition of the Pangolin Seminar. I'm just opening the tab here in my computer. So I always like to advertise the next edition before finishing the recording. So the next edition of the Pangolin Seminar will take place in 2 weeks' time, on the 18th of May. And Barbara Nelli from the Universidad dell'Aquila will be speaking to us about the topology of constant mean curvature surfaces with convex boundary. So hope to see everybody there in 2 weeks' time. So I'm going to end the recording now.